Hello, student. So we will start the session, and I will share the screen. Okay. So here we are going to simulate BPSK. Okay. We are going to simulate BPSK bit error rate performance. Actually, we are going to see the bit error rate performance in AWGN channel. Okay. AWGN channel using Matlab. Okay. So we are going to analyze the BPSK bit error rate performance in AWGN channel using Matlab. Okay. So I think you know what is BER. Okay. So that is bit error rate. Okay. So bit error rate is defined as number of error divided by the total number of bits. Okay. So this is number of error. Okay. Divided by total number of bits. Okay, so this is the bit error rate. Okay, for example, if you are sending 100 bits, okay, 100 bits from some place to another place, okay. So you will receive the 100 bits, okay, and 1 bits you received as you receive as incorrectly. Okay, you received incorrectly 1 bit. Okay, for example, if you send 0 here, you will receive 1 instead of that 0. So this happened a bit error. Okay, so bit error is happened. Okay, so we have sent 100 bits. So total number of bits is 100, and 1 bits we received incorrectly. So 1 error. Okay, 1 bit error. So our bit error rate is 0.01. Okay. So this is the bit error rate. Okay. Actually, we also call this probability of error. Okay. Probability of error. Because this is also error probability. No? The error divided by number of bits. So it will be a probability of error also. Okay. So that is bit error rate. Okay. So we have seen that. Okay. So if I go the simplified Bpsk modulator, okay, we have discussed this in previous session also. Okay, simplified Bpsk transmitter. Okay, so it will look like this. Okay, so we have message signal. Okay, so it is a random bit stream. Okay, so this will be our message signal. Okay, so this will be our message signal, message bits. Okay, message bits, and we have to line coded this message signal. Okay, so for BPSK we normally doing in practically. Okay, practically we normally doing bipolar NR reset mapping. Okay, bipolar NR reset mapping. Okay, so this is the line encoder. Okay, so here if you have 0, if you get 0 bit, okay, you will assign some minus voltage value for this 0, and if you have 1 value, you will assign plus voltage value for 1. Okay, so in BPSK, I think you can remember that this voltage will be root TB. Okay, we set this voltage to root TB. So this EB is the bit energy of the bit. Okay, 1 bit energy, EB is the bit energy. Okay, so in BPSK, you know that bit energy, okay, bit energy is also equal to symbol energy. Okay, it is in BPSK, but in higher order modulation, this will not same. Okay, normally the bit energy will be lower than the symbol energy. Okay, so we set, so if 0 is there, we will generate minus root EB voltage. If 1 is there, we will be generating, okay, we will be generating positive, okay, plus root EB voltage value. Okay, so we have the line coded signal. Okay, we have the line coded signal. Okay, so here we have plus or minus root EB. Okay, and here we are doing the modulation. Okay. So in BPSK we are using a product modulator. Okay, so we have a basis function. Okay, so in BPSK, you know that only one basis function is used. Okay, it is equal to 2 TB cos 25 FCT, as I can remember. Okay, so this FC is the carrier frequency. Okay, for example, in 4G LTE, okay, SLT use 200, 600 megahertz band. Okay, so this carrier frequency will be this. Okay, this band. Okay, in SLT, 4G LTE network in SLT. Okay, so what is the output here? The output will be plus root EB 51T. Okay, so that is for 1. Okay, or minus root EB 51T, that is for 0. Okay, so this will be your transmitting waveform. Actually, this is the transmitting waveform. Okay, this is the transmitting waveform. Okay, waveform. So here you are transmitting sinusoidal signal, sinusoidal wave. Okay, sine wave, sinusoidal wave in RF range. Okay, in RF range. Okay, so this will be a real signal and it will be an energy signal. Okay, it should be an energy signal. Otherwise, we can't propagate it. We can't transmit it. Okay, so it will be a real signal and it will be an energy signal. Okay. 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 So these are the two waveform. So we will have two waveform, two signal to transmit for 1 and for 0. Okay. So you know that here we have 0 phase shift and here we have 5 phase shift. Okay. Here we have 0 phase shift and here we have 5 phase shift. Okay, for this signal. Okay. So so this is the transmitting waveform. Okay, so we are transmitting this through air, through free space. Okay, we can directly feed this signal to antenna. Okay, antenna. Okay, then antenna will propagate this signal. Okay, so you know that. So we are considering a AWGN channel. Okay, so you when this channel is propagating, some noise can be added. Some noise can be added to this signal. So that noise is called AWGN, additive white Gaussian noise. Okay, so it will be a Gaussian variable. Okay, Gaussian number. Okay. Okay. So actually we have discussed these things. Okay, we have already discussed these things. Okay, so the signal will be transmitted then at the receiver. Okay, so let's say that this is the received antenna. Okay, so here we have the receiver. Okay, so this will be our received antenna. Okay, and so this signal will received here but the received signal will also have some noise component. Okay, so this will be the transmitted signal, that is plus or minus root TB 51T. This is the transmitted signal, and some noise will be added to this signal. Okay, so this will be the received signal at the receiver. Okay, let's say it Rx received signal. Okay, okay. So now you can see that. Okay, now you can see that. Okay, we are going to send root EB or minus root TB. Okay, okay, so I will discuss the other things also before come to this point. Okay, so now we are going to so this is BPSK transmitter. Okay, so this is BPSK transmitter. Now we are going to discuss the BPSK receiver. Okay, this is also simplified BPSK receiver. Okay, simplified BPSK receiver. Okay, so so we will we will be receiving this kind of signal. Okay, root EB plus or minus root TB 51T plus N. Okay, so plus root TB for 1, minus root TB for 0. Okay, you already know. Okay, so in this stage also we have another product modulator, product demodulator. Actually, this is, we can call this a demodulator. Okay, and we have a basis function again here. Okay. Okay, so here the received signal will be multiplied by the basis function again. Okay, and the output will be fed to a integrator. Okay, to an integrator. Okay, so the integration will be done 0 to TB. What is this TB? This TB is the bit duration. Okay, so this TB is the bit duration. Okay, and in BPSK it is equal to symbol duration also, because one bit have one symbol has one bit. Okay, so this bit duration and symbol durations are same. Okay, so we are going to integrate 0 to TB this multiplied signal. What is the multiplied signal? 51T Rx. Okay, so this will be our multiplied signal. Okay, so what is the output here? Can you guess? What is the output here? Okay, we will see. Okay, so another thing I forgot to tell you, that this is a orthogonal signal. No, not orthogonal, actually orthonormal signal. This is a orthonormal signal. This is orthonormal signal. Okay, okay. So that means energy of the signal will be equal to 1. No, 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 no. Orthogonal means yeah, this is orthonormal signal. Okay, so this is orthonormal signal. Okay, so so you know that. Okay, so output of this point, the point of the signal of this point will be plus or minus root EB. Okay, so signal in this point. Okay, signal in this point. Okay, that will be plus or minus root EB. Okay, 51T. Okay, okay, and plus N naught. Okay, oh, again this is multiplied by 51T. Okay, this is multiplied by 51T. Okay, this is again multiplied by 51T. Correct? Okay, so the input signal here will be the input signal to the integrator will be this. Okay, and we are going to integrate this 0 to TB. Okay, so what is the answer here? So what will be the answer here? So if I expand this, we will be having, so this is plus or minus, okay, plus or minus root TB, it is a constant, so I can get it out. And here from 0 to TB, I have evaluate phi 1t into phi 1t, that means phi 1 square t, okay, dt plus this noise, okay, 0 to TB, this noise phi 1t, okay. So what is the value of this? Okay, what is the value of this? This will be 1 because this is orthonormal, okay. The energy will be equal to 1, okay. Energy of the signal will be equal to 1, okay, because it is an orthonormal signal. So you will be having here plus or minus root EB plus this is some value related with the noise, no, okay, related with the noise. Let's say that is N naught, okay. So this, you know that this noise is AWGN, Gaussian variable. So this N naught also will be a Gaussian variable, okay. We can assume that this N naught also is a Gaussian variable, so that is related with the noise power, okay, that is related with the noise, okay. So this N naught will be a normal Gaussian function with 0 mean and sigma square variance, okay. So this sigma square is the noise power, okay. So we have already seen this, okay, we have already seen this. Actually we have generated this signal and see what is happening, okay, when we are increasing and decreasing this noise power, okay, we have already seen that, okay. Okay. So now what is the problem? Now what is the problem? Okay. So now you can see that we are sending, so we are sending plus or minus root TB. Okay. So strictly speaking, we are sending plus root EB. Okay. We are sending plus root EB for 1. Okay, minus root TB for 0, okay, for 0, okay. But when you are transmitting, so this will be your transmitting symbol, okay. So this will be your transmitting signal, okay, okay. And what is the received symbol? You will receive this, no, you will receive this after the integrator part. You will receive this, that means you will receive plus root EB plus N naught or minus root TB plus N naught, okay. So you can see that now you have sent some value 1 and 0, but now it is not same, it is different, okay. So here you have to decide whether this signal, whether these received symbols are 1 or 0, okay. You have to decide it, okay. To decide it, you have to use a decision boundary and you are decoding it, okay. So so you know that in BPSK, okay, BPSK, we have our consolation diagram is this, okay. So this will be minus root TB and this will be plus root TB. So these are our symbols, okay. So these are the symbols we are transmitting, okay. So due to this noise addition, this so we will not receive the same symbol, okay. So symbol will be any of this area, okay, any of this location, okay. We don't know, okay, we don't know. Anyway, we have to decide that whether the received signal is belongs to plus root TB, that is belongs to 1, or belongs to minus root TB, that is for 0. We have to decide it. For that we use decision boundary, okay. So this decision boundary is has the same distance from has the same distance to this side symbol and this side symbol, okay. So it should have the same distance, okay. because these are equal probable bits. Okay, so otherwise this decision points will be changed. Okay, so to calculate this decision point is actually a very mathematical things. Okay, so we have to use very complex mathematics, very complex probability theory. Okay, we have to concern on very complex probability theories to calculate this position, this boundary. Okay, but these are equiprobable and symmetric signal, symmetric symbols we have. Okay, so we can use we can simply decode this middle point as the optimum decision boundary. Okay, so this middle point will be 0. Okay, now you can decide it based on this boundary, based on this 0. Okay, so how you decide it? Okay, so you can decide if the received symbol is greater than or equal to 0, you can assign that bit, that received bit is equal to 1. Okay, equal to 1. So that is your decoded signal, actually decoded signal. Okay, so let's see that it is a detected, okay, detected symbol. Okay, so if Rx received signal is greater than 0, detected bits is, you can assign detected bit is to 1. Okay, if the Rx the received symbol is less than 0, you can assign this, so this detected bit to a 0. Okay, likewise you can decode the signal. Okay, so here after this integrator, you have a decision stage here. You should have a decision stage. Okay, so here okay, so here you are going to decide, okay, the bit, okay, the received bit. Okay, so you are decide the bit, or you are decode the bit based on a value decision boundary. Okay, based on the value. Okay, actually this is called hard coding. Okay, hard decoding, this is called hard decoding. Okay, okay, so you make your decision based on a value. Okay, so Rx is greater than or equal to 0, you decide your detected bit is 1. Okay, or Rx is less than 0, you decide your detected bit is 0. Okay, so that will the decoded signal. Okay, so this is called actually hard coding. Okay, this is hard decoding, this is called hard decoding. Okay, so now you have detected the bit as 1 and 0. Okay, okay, so now you can understand. So that is the block diagram. Okay, so that is the required stage for our simulation. Okay, that is those are the required stage for our simulation. Okay, so this can be this is actually a simplified BPSK transmitter. All the stages are not here, all the stages are not mentioned here. Okay, okay, so now so okay, okay, so now okay, you can see that we have already discussed that. I'm going to repeat it again. Okay, so we are sending some value plus or minus root TB. Okay, but we received another value plus or minus root TB plus N naught. Okay, okay, so for 0, for 1, you are sending this kind of plus or minus root TB value, and you will get random values here, because this is a random variable, and also this will be a random number, so you will get some random numbers. Okay, so based on this random numbers and your decision boundary, you have to detect the bit is 1 and 0. Okay, So there may be a probability, okay, there may be sometime, okay, sometime sometime you may detected +1, so you may detected 1 as 0 or 0 as 1, okay. So it gives us a error, no? It gives us error, okay. So it can be happen, no? Here it can be happen because we are going to decide the received signal based on the decision boundary, okay. So sometime the received signal can be shift to other side also, other region also. In that case, we will be decoding it wrongly, incorrectly, okay. So there can be error, okay, error can be happen, okay. Okay, so actually based on so you can see that when we are increasing this value, okay, when we are increasing this value n naught, actually when we are increasing this value means we are increasing the power of the noise signal, okay. So this is related with the power, okay. So if we are increasing this value, that means we are increasing the power of the noise signal, okay. We are increasing the power of the noise signal, okay. Okay, so if we keep this, okay, so this will be our signal. So this is the received signal, okay. So this will be the received signal plus or minus root TB plus N naught, okay. So this will be our signal power, signal component, okay. So this will be our signal energy or signal power, and this will be our noise component, okay. So it is related with the noise power, okay. Let's say that signal power is S and noise power is N, or let's say that sigma is square, okay. Why I say like this, sigma is square, okay. You can remember that. So this N naught is a Gaussian noise, okay. So this will be a 0 mean sigma square variance random variable, okay. So this sigma square is related with the noise power, okay. So this related with the noise power, we have simulated this, okay. We have simulated this in our last session, okay. So we see what happened when this noise power is increasing. When we are increasing this sigma square, the noise power is increasing. Then we see the effect, we see the impact on this received signal, okay. We have already seen this, okay. So I can say that this is the noise power, okay. So okay. Okay, this will be our noise power, okay. So keep this in mind, okay, keep this in mind, okay. And we will start the simulation. At the simulation, I will explain what we are going to do again, okay. So now in our simulation, we are going to, so the most important thing is this, okay. We are going to have this signal, okay, our message signal, let's say that is MI, okay. And we will have this bipolar mapping, okay, bipolar mapping, bipolar NRZ mapping, okay. So we will use this as our transmitted symbol, okay. We are not actually, this is the transmitted symbol, okay. We have generated this waveform, but in this simulation we are not going to generate these symbols, okay, these waveforms, okay. So this is our transmitted symbol. We can say that this is our transmitted signal plus or minus root TB, and here this will be our received symbol. What is the received symbol? Plus or minus root EB plus N naught, okay. So that will be our received signal, okay, received symbol, okay. So we use this one, okay. So this one will be our transmitted signal. This one will be our transmitted symbol, okay. Let's say that TX symbol, transmitted symbol, so that is Tx. Okay, so we will have some transmitted symbol. Okay, and in simulation we select this root EB to 1. Okay, we select this root EB to 1. Okay, so root EB is equal to 1. Actually we set symbol energy for 1. Okay, we set, okay, actually we are going to set, okay, so here we are going to set symbol energy ES, oh, that is equal to bit energy EB to 1. Okay, so root TB also will be 1. Okay, so we set our symbol energy to 1. So that means we are going to set our bit energy to 1 also. So that means root TB will also 1. Okay, so so we set our symbol and energy to 1. So we will have here -1 no +1. Okay, so this will be our transmitted signal. Okay, symbol -1 no +1. Okay, this will be our transmitted signal. Now we will transmit it. Okay, so we will simulate this. Okay, we will achieve this is two-stage in Matlab. Okay, so we know that CLC clear all. This is for clear our workspace. Okay, and we need to first generate the message signal. Okay, so we need to first generate this message signal. Okay, so I take this as mi, so I will generate that message signal. Okay, so my message signal m, we no need to use I here. Okay, so I use we already seen this. I use friend I Matlab code. Okay, and the value should be 0 to 1. Okay, value should be 0 to 1. Okay, and the size will be, okay, so this is we will get the 1 row and several bits. Okay, so I put capital N here. Okay, okay, so that is number of bits. N is the number of bits. Okay, capital N is the number of bits. Okay, so I will define it here. Okay, so at this moment I will take 100 bits. Okay, so here I am going to generate, sorry, here 0 and 1. I'm going to generate 0 and 1 integer, 100 number of 0 and 1 random combination. Okay, so that will be my message signal. Okay, so this is the message signal. Okay, so here we generate the message signal. Okay, message signal. Okay, now our message signal is okay. Now we move to next point. What is the next point? Okay, so so we are going to generate our transmitted symbol. Okay, so transmitted symbol will be -1 or +1. Okay, because we set this root TB to 1. So this root TB to 1. Okay, so we are going to have -1 or +1 transmitted symbol. Okay, so we can say that it is BPSK mapping. Okay, so sometime in programs you can see that this is as BPSK mapping. Okay, actually this is not the BPSK mapping. Okay, we just assume that this is our symbol, transmitted symbol. Okay, but actually these are not the transmitted signal. Actually we are sending some energy signals. Okay, but here we are not going to generate or not going to consider that energy signals. Okay, waveform, we are not going to consider that waveform. Okay, so here you can see that I have to generate this mapping. I have to do this I have to generate this symbol based on the 0 and 1. Okay, so I put the for loop here. Okay, so for I is equal to 1 to n. Okay, 1 to n. Okay, I assign So this is my transmitting symbol. Okay, TXI as 1. Okay, I as 1. If the message bits MI is equal to 1. Okay, if the message bit is equal to 1, I set my transmitted symbol to 1. Okay, otherwise that means the message signal is 0. Message bit is 0. Okay, if the message bit is 0, my transmitted symbol will be -1. Okay, so actually this is like a bipolar line coding. Okay, this is just like the bipolar line coding. Okay, so this will be my message signal. Okay, so if I run this, okay, yeah, I have to put another in. Okay, so if I have run this, okay, so you can see that okay, so here you have to put, so this will be, so here also simple tx. Okay, so put it. Okay, so what happened? So it should be okay, no, now okay. So you can see that now this is our message signal. Okay, we have 100 bit 0 1 0 0. Likewise, we have random sequence 100 bit sequence. Okay, so in BPSK mapping, I map this 0 to -1, this 1 to 1, 0 to -1. Likewise, so this TX should be -1 1 -1 -1. Okay, so if I, okay, so you can see, no? -1 1 -1 -1, so on. So this will be our transmitted signal. Okay, so now we are transmitting this signal. Okay, now what happened when we are transmitting the signal? Okay, when we are transmitting the signal, okay, the noise can be added to that transmitted signal. Okay, 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 so we are transmitting here, we are transmitting here 1 or plus or -1. Okay, when it propagating, some noise component can be added. Okay, so this is a AWGN with 0 means and some power sigma square. Okay, so so this will be my noise variable. Okay, so now I am going to generate that noise signal and I add it to my transmitted symbol. Okay, plus or -1, then I can create the received signal. Okay, now I am going to get the received signal. Okay, now I am going to get the received signal. Okay, so simply we can do it like this. Okay, so I can generate some random value. Okay, AWGN value. So you already know that how we can generate it. Okay, so we use is the norm. What is the, so in previous section we have seen that what is the code, random number Gaussian random variable in Matlab. Okay, so this will be our norm rand, no? So this will be our signal. Okay, okay, so we will have AWGN as norm rand. Okay, norm rand. So in AWGN the mean will be 0. It is a 0 mean random variable, and we have some sigma value. Okay, so I put it as a sigma. Okay, so what is this sigma preferred? This sigma referred to the power. Okay, so actually the sigma square referred to power. Okay, okay, so I can here I can assign this sigma. I can assign some value to this sigma. Okay, so so sigma is 2, so power will be 2 square, that means 4. Okay, so here I can generate this kind of random variable. Okay, then okay, so this random variable will be add to my tx symbol. Okay, so this will add to my tx. Okay, okay, and that is my received bit rx. Okay, that is my received bit. Correct. Okay, so this will be my received bit. Correct, very simple. Okay, so so actually here this one. Okay, so I write here this one. Okay, right here this one. Okay, so this plus or minus will be my tx. No, tx is plus or minus. Okay, so I have added some Gaussian variable, Gaussian noise. Okay, and this will be my received signal. Okay, okay, so this will be my received signal. Okay, so this will be not received signal. So if I see the received signal, okay, so you can see that my tx signal, I have 1 1 0 minus 1 minus 1, so 1 and minus 1 is there. But if I look at the received symbols, okay, received symbols, so you can see that now it has 2 2 0 0.2 0 0.2. Okay, so there are some values. Okay, there are some values. So these are my received symbols. Okay, now I have to check whether, okay, now I have to check whether these symbols are 1 or 0. Okay, this is 1 or 0. So you can see that. So now now where we are? Now where are we? Okay, now we are here. No, now we are here. Okay, now we are here. We are here in this point. Okay, so we have Rx. Okay, so this is this. No, okay, we have Rx, and that is equal to plus or minus root TB. So we have set this root TB to 1. So plus or minus 1 plus n naught. Okay, so we are in this position. Okay, now, okay, so we have generate the message signal. We have generate the BPSK symbol. Now we had sent it to a Gaussian channel and some noise added. Okay, and some noise added, and then we decoded it. Then we get our received symbol. Okay, so this will be our received symbol. Now we are here. Okay, actually we didn't consider this waveform generation and other things. Okay, we only concern on this stage, this stage, and now we are going to look at this point. Okay, that is enough. No, you can understand that is enough. We no need to generate the symbol signals and other things, because we are going to analyze the bit error rate performance. Okay, okay, so now this will be our received symbol. Okay, received symbol. Now we are here. Now we need to use this hard decoding part. Okay, so that is our decision making stage. Okay, so we have to make a decision whether this received symbol is 1 or 0. So how we can do it? We are do it based on our decision boundary 0. Okay, and if our received signal is less than 0, okay, less than 0, so I assign it to this side. Okay, that means to 0. If the received symbol is more than 0, higher than 0, I will assign this to this region, this side region. That means to 1. Okay, so that is what I'm going to do. Okay, so that one, for that one also I need the for loop. Okay, and also you can see we have to use this simple mapping also. Okay, simple conditional statements also there. Okay, so I can write as for I for I equal 1 to n, okay, 1 to n. So I can see that if my received symbol Rx is Rxi, okay, so this is my received symbol Rxi, okay, greater than Rxi is greater than or equal to 0, okay, greater than or equal to 0. Greater than or equal to 0 means this side, no, this side, okay. So the received symbol is greater than or equal to 0. That means if this region, the received symbol is in this region, I will assign it to 1. Okay, so that will be my detected bit. Okay, so my detected bit, I assign it to 1. Okay, okay. If not, that means the received signal in this area. So if it is not so, if it is not greater than or equal to 0, I will assign the received signal to here. That means my detected bit to 0. Okay, so that is what I'm going to do. Very simple. Okay, so now the received signal is greater than or equal to 0. Okay, I put so my decoded bits. Okay, so I will do decoded bit. This is my decoded bit. Okay, decoded bit is equal to 1. Okay, because it is greater than or equal to 0. If not, that means the Rx, the received symbol is less than 0. If so, I assign that bit. Okay, I decide that bit as 0. Okay, so this will be my decoding. Okay, so this will be my decoding. Okay, so I have decoded bits. Okay, so this decoded bit also we should have 0 and 1. Okay, so if I see this, okay, see this, okay, so this will be my decoded sig. db, sorry, not db, so this one, no, decoded. So you can see that it is again 0 1 0 1 0 1. Okay, okay, so this will be my decoded sig. Okay, so you can see that, okay, you can see that, okay, so here I use very small power. Okay, I use very small power. Okay, so maybe this bit not change, all bit may be decoded very well, there is no error sometime. Okay, so to see that, to check the okay, now we have decoded this. Okay, so we have decoded this, and sometime error can be happen, no, we have discussed it, sometime error can be happen, we don't know. Okay, when we are at this decoding point, at this decision point, okay, at this decision point, it leads to happen some error. We have explained it here. Okay, because we transmit root TB, not here, not root TB, plus or minus 1. Okay, and we received plus or minus 1 plus some noise random variable. Okay, so we have decoded this first 1 and 0, and sometimes it can lead to error. No, it can lead to error, we don't know. Okay, now how to see this, how to see this, whether there is a error or not, what we should do. Okay, so this is my detected bit, okay, and this will be my transmitted bit. No, this will be my, so I can directly compare it with the message signal. No, okay, so this message signal I have transmitted, so this detected also we have detected the message signal 0 and 1. Okay, so this will be my decoded detected signal, DEC, decoded signal, and this M is my message signal. So I have to compare this message signal and detected signal. Okay, so you can see that message signal is 0 1 0 0, and you can see here if I get the decoded signal, it is also 0 1 0 0, but maybe in other position, maybe sometime 1 or 2 bits may be changed. Okay, okay, to check that we have to compare it. We have to compare it. Now I am going to do that comparing part. Okay, now I am to do that comparing part. Okay, I am going to find whether there is any error happen. Okay, so I am going to find whether there is any error happen. Okay, so I am going to find the number of error. We don't know, sometime maybe no, there is no any error. Okay, anyway, we are going to get this number of error. Okay, so how we can do this? Actually, you can do this. Okay, so try to do your own code for this one. Okay, so you can do this. Okay, so I am going to compare this. Okay, so I can use the same I, no issue, because in any every for loops it is updating. Okay, so I can use I for any as an index. Okay, I as an index. Okay, if you are not comfortable, you can choose different index. Here I, here K, here maybe I or something. Okay, so but here it will not affect to our program much. So I am going to use the same index. Okay, now for I equal 1 to n, I am going to compare my detected signal with, okay, I am going to compare my detected signal with the message signal. Okay, how can I compare? Okay, I am going to compare these are equal or not. Okay, if this is equal, okay, if this is equal, okay, so this is my transmitted, so this is my message bit. It may be like somewhat like this. Okay, and so we have some value. Okay, and this will be my detected bits. Okay, it will be 1 0 1 0 0 0 1, so on. Okay, now I am going to compare. Okay, so I going to compare this one and this one. So if these are equal, there is no error. If this one and this one equal, there is no error. This one and this one equal, no error. This one and this one, no error. So this one and this one, if it is equal, no error, but here it is changed. Okay, so there is one error. Okay, so here number of error is equal to 1. Likewise, you have to compare all the value. So if you have any bit change, it is not compare, again this will be update up to 1. Okay, okay, so actually we have to concern on if it is equal, this M and decoded signal, message signal and decoded signals are equal, we no need to worry. But if it is not equal, we have to add, we have to increase the number of errors. No, we have to increase the number of error by 1. Okay, so I can do it very easily. Okay, so I am going to compare if, okay, if my decoded signal DEC I is not equal to, I can type like this. How, where is that? Yeah, this one. Okay, this is not equal sign. Okay, this sign equal 0, this is not equal. Okay, so if my decoded symbol is not equal to my message signal, okay, we have number of error, we have to increase by 1. Okay, we have to increase the number of error by 1. Okay, by 1. Okay, that is the thing we have to do. Okay, so that is sent. Okay, so if it is equal, we no need care, but if it is change, we have to increase this number of error by 1. So here we are having a loop. Okay, so say that you have one bit change, so number of error will be So here we have to assign here first number of error should be equal to 0. Okay, should be equal to 0. Okay, now when this for loop begin, it compare this decoded bit and this message bit. Okay, so if the message bit is not equal to 1, so this number of error, now it is 0, it will be increased by 1. So now number of error is 1. Now again it is checking. So if you have any point, the mismatch point, again this will be increased by 1. Okay, now number of bit error is 2. Likewise, it will compare all the elements, all the corresponding elements, this decoded bit array and the message bit array. If there is mismatch, it is increased by 1. So you can calculate the number of error like this, correct? Okay, so let's see. What's that? Okay. We have to put another in. Okay, okay, so you can see that. Okay, so you can see that. So this is BPSK mapping. Okay, actually this is transmitted signal. Okay, this will be the transmitted signal. Okay, signal. Okay, and so here we are transmitting the signal. Okay, here we are transmitting the signal. Okay, we are transmitting the signal in AWGN channel. Transmitting the signal symbols in AWGN channel. Okay, channel. Okay, and your received signal will be the addition of transmitted signal and symbol. Okay, transmitted signal and noise. Okay, so this is the transmission. Okay, so after received, we have to decode. Okay, we have to decode. So this is at the receiver. Okay, so this is at the receiver. So at the receiver, okay, at the receiver, we received Rx. Okay, we received Rx. Okay, we received Rx, and the symbol, received symbol, that is Rx. Okay, received symbol Rx is decoded. Okay, is being decoded. Okay, is being decoded with decision, with the decision boundary. Okay, boundary. Okay. So this is actually hard decoding. Okay, so this is hard decoding. Okay, so now we are going to do this. Okay, so we are decoded the signal here. Okay, after decoding, now we are calculating number of error. Okay, here we are calculating number of error. Here we are going to calculate in the number of error. So let's see what happened. Okay, so number of errors are 57. Okay, I can't believe that one. Okay, so maybe that means there are 57 bits change. Okay, there are 57 bits change. Okay, so if I put this very small value, let's say that 0.2. Okay, so this number of error should be reduced. Okay, because this signal power is reduced now. Okay, so this number of error should be reduced. Let's see. Now it is 0. There is no any mismatch. All the decoded signal, decoded symbols are, decoded bits are same as the message bits. Okay, there is no error. Okay, so if I put somewhat higher value, 0 to 5 point, maybe there can be some number of error. Still no. Okay, let's put this up to 9. Still there is no any error. Okay, if I put round 1, yeah, it is still not, there are no any uh, uh, power. Okay, there are no any error. This is still not. Okay, so let's do. So now you can see that when we increase it to 2, the number of error will be somewhat high. Okay, so if I put 5, okay, it should be very high. Okay, it should be very high. Not very, again, it should be 45. Okay, maybe that is randomly happen. Okay, so sometime the big decodes can be the bits can be decoded correctly. Sometime the decoder can't be decoded correctly. Okay, so it is a random things. Okay, so let's put it up to 10. Okay, so that means very high power, noise power. Okay, but again, you have 39 bits, 47 bits. Okay, so when you are simulating, you can see that values are changing because this is happen randomly. Okay, so this is a probability. Actually, this is based on the probability. So every time we didn't get the same value. Okay, so if we put some very big value, maybe, okay, let's say it's 100. Okay, so you can see that this sigma, let's put some value. Okay, so we will have some higher value. Okay, we don't know. Okay, anyway, you can see that if we are changing very high, okay, it is not come up to 50. No, okay, you can see it. Okay, so actually that is very important. Okay, that is the probability actually. Okay, so you can see that. Okay, when we are changing this sigma to 0 to 1, 0 to 1, we are having some little error with little number of error. Okay, but when we are getting it up to 2 to any value, we will have only 50. Why it happened? Because it is not increasing. Why it happened? Okay, actually that is based on the probability. Okay, so you are generating what is that? You are generating what is called this message signal. You are generating remember, is this called the random variable? Okay, using rand I. What the uniformly distributed. Okay, uniformly distributed value. Okay, so 1 and 0 will have half probability. Okay, so 1 we have half probability and 0 we have half probability. Okay, so here we are going to 1 and 0, we are decoding, we are generating all based on 1 and 0. Okay, so you will have only half probability. Okay, you will be having only half probability. So if you decode it 1 as 0, okay, so generally you will be having half probability. Okay, so that is why when we are increasing this sigma, this noise power to very high, still the still the the still the number of error will be 50. If we are sending 100 bits, okay, the 50 bits will be approximately 50 bits will be wrong. Okay, okay, so that is because the uniform distribution. Okay, that is because the uniform distribution. We will not having 70, 80, 100 number of error. Okay, so we will be having maximally with near 50 near values. Okay, because we have half probability. The error can be the error probability also will be half. Okay, okay. So I think you get it. Okay, you get it. So that is why when we are increasing the, when we are sending 100 bit, and if it is 50 bits are incorrect, that is we can't do a communication there. Okay, we can't do a communication there. As I can remember, if we are sending 10 lakhs bit, only one bit can be error. Okay, for a good communication channel. Okay, otherwise that channel is not good. Okay, okay. So 50 bits wrong means 50 bits error means the all bits are error. Okay, so there are no any information, the signal is error, you will receive the error signal. Okay, okay. So I hope you get this. Okay, so we are calculating the number of error here. Okay, we are not calculating the bit error rate. Okay, so you can see that bit error rate is nearly half. Okay, if we are getting very high power, noise power, the bit error rate will be very high, and it is equal approximately to 50. Okay, I think you get it. Okay, if you have any problem you can ask. Okay, so bit error rate is nothing but number of error divided by n. Okay, so this will be the bit error rate. Okay, so bit error rate here it is 0. We will have again 0. Okay, because we are using 1 here. Okay, let's put some 10 value. Okay, so you will get nearly 15. Okay, yeah, 15, no, 50. That means 0.5. That means nearly 50 bits are incorrect. Okay, so you will get nearly that value. Okay, every time, every iteration, you will get nearly that value. Okay, so is that okay? Okay, so are we finished now? No, still we are not finished. Okay, so now we have calculate the bit error rate. Okay, now we have calculate the bit error rate for some sigma value. Okay, for some sigma value. Okay, okay. Now, so what here we so now you can see that. Okay, okay, we have set our bit or bit energy or symbol energy to 1. Okay, so we have set it to 1. Okay, so our transmitted symbol will be plus or minus 1. Okay, so if it is plus, it is 1. If it is minus, that means it is 0. Okay, okay. So our transmitted symbol will be plus or minus 1. Okay, so this will be transmitted signal, and our received signal will be, okay, transmitted signal plus noise. Okay, so this will be the transmitted signal plus noise. Okay, so this will be my received signal. Okay, and when we are decoding based on hard decoding, okay, so if this Rx is greater than or equal to 0, I put my detected bit as 1. Rx is less than 0, I put my detected bit as 0. Okay, so here it can lead to happen some errors, number of errors. Okay, number of errors, and if you divide that number of error by n, you will have bit error rate. Okay, bit error rate. Okay, so now this bit error rate happen to some n value. So this is power. Okay, this is the power, and it is equal to sigma square. Okay, so this will be the noise power. Okay, so this bit error rate, number of error, will based on the power of this noise component. Okay, power of this noise component, and it is equal to sigma. Okay, so you know that this n is a Gaussian variable. Okay, it is a normal Gaussian variable. Okay, with 0 mean and sigma square. Okay, okay, with this variance, and this variance is related with the power, okay, related with the power, okay. So we are changing the sigma and we get some bit error rate value, okay, okay. Now in bit error rate performance, actually, okay, bit error rate performance, okay. Now tell me, so you can see that if I get the SNR value, okay, if I get the SNR value, so SNR will be my transmitted symbol power S, okay. So this is my transmitted symbol power, and it will be it should be divided my noise power. So noise power I will put as sigma square, okay, because the power of this noise is sigma square, okay, okay. So this is the noise power, okay. So this will be SNR, okay, okay, okay. Now you can see that our transmitted energy, transmitted signal energy, we set to 1, okay. So that means we can assume this transmitted signal power is 1, okay, S equal to 1. So SNR will be 1 by sigma square, okay, 1 by sigma square. Now I am changing this square, okay. So if I high this, if I higher this sigma, that means I am going to I am going to increase the noise power, okay, noise power. So SNR will be reduced, okay, SNR will be reduced. If I reduce this noise power, if I reduce this noise power, SNR will be increased, okay. So this will be the SNR, no? So the SNR will be 1 by sigma square, because I assume I set my transmitted symbol energy to 1, okay. So SNR will be 1 by sigma square, okay, okay. So I am changing this sigma means I am changing the SNR, okay. So you know that if we have higher SNR value, that means we have good channel, okay. For higher SNR value, our signal power is high, our noise power is low, okay. So if we have SNR, higher SNR value, okay, so it will be very good, okay. If we have low SNR value, so it will create some issue, it will create some bit error, okay, it will create some bit error, okay. So normally this SNR is referred, okay, this SNR is represented in dB, okay, this represent in dB, okay. So SNR dB is equal to, I just put 10 log 10 is 1 by sigma square, okay. So this is my SNR dB value, okay, okay. If I change in this sigma, I am changing this SNR value, okay. I am changing this SNR dB value, okay. So in practically, okay, for example, for 4G LTE network, okay, the maximum SNR value we can achieve this 32 dBm, okay, as I can remember, okay. And so if it is between 20 to 25 dBm, we said that this is a very good, we have a very good coverage, okay. So we will be having very high data rate, okay. Here this is the maximum value, so we will get in the maximum data rate here, okay. But very rarely we can achieve this one, maximum rate. Actually, as I can remember, that is the highest SNR value I could be observed in a practical site, okay. Maybe I'm wrong, okay, other can see more than this one, but this is the highest dBm value I can get, I could see, okay, okay. So and it is around 20-25 dB, okay. So this is very good SNR value, okay. So it is if it is 16 dB, if it is less than 16 dB, So it is not much good, okay, but still we can achieve some performance, okay, but it is somewhat not good, okay. So what is SNR dB is 0 means, okay, 0 means, that means signal power and the noise power are same, that is the 0, no, so here you will get 1, so that is 0, okay, the signal power and noise power will be same, okay. And if you have so if the SNRDB minus value means your signal power is very less than the noise power, so minus value in SNRDB minus value, there is no any communication happen, okay. Actually 16 dB, we should have at least 16 dB SNR dB for a good communication, for a appropriate communication, okay. So you can see that the based on SNR dB value, okay, our bit error rate will be changed. How it change? When we are changing the SNR dB value, we change the sigma, okay, we change the power, okay. So if we change the power, okay, if we change the power, this received signal also can be subjected to change, okay, so that it will create the error, okay. So that is the thing you should understand, okay. So finally you can see that, okay, so analyzing this result, okay, you can conclude that when we are changing SNR dB value, it change the sigma square, that is noise power, okay, and it will change the bit error rate, okay, bit error rate. Actually, we analyze bit error rate. We analyze this bit error rate with respect to SNR dB, okay. So we analyze the bit error rate with respect to SNR dB, okay. That is our bit error rate performance, okay. So that is we called our bit error rate performance, okay, bit error rate performance, okay. So normally, okay, so our SNR dB will be the independent variable, okay. We change SNR dB value, okay, and we check what happened to bit error rate, okay. So very low bit SNR value, we will have very high bit error rate, okay. It is up to 50 around, okay. So when we are increasing the SNR dB, the bit error rate also should be decreased like this. When we are increasing SNR dB, bit error rate should be decreased, because we are increasing SNR means we are reducing the noise power. So that means our bit error rate should be less, okay. So at some value, this bit error rate will be 0, okay. So you will be having this kind of curve, okay. You will be having this kind of curve, okay. So with this point and the rate of change, okay, we are analyzing the bit error rate performance, okay. So that is the idea, okay. Now we need to actually, when we are analyzing bit error rate performance, means we have to plot bit error rate value for different SNR dB value, okay. So that is the idea. We have to get separate SNR dB value, okay. So this SNR dB from 0 to 40, I think it is good value, okay, because if it is less than 0, there is no effect. The bit error rate will be very high. It is equal to 50, okay. And at 30, 40, okay, you will be having 0 bit error rate, okay, because here the bit error rate is very low in this range, okay. So SNR dB value we can get from 0 to 30 dB value, okay, and we have to calculate the bit error rate for all these SNR dB value, and we can plot, Okay, that is the normal protein. No, that is how we draw a graph. Okay, now we are going to draw a graph. Okay, so our independent variable will be SNRDB. Our dependent variable will be BER. Okay, so we will see how to do it. Okay, now here we change the sigma value by manually. Okay, we change the sigma value by manually. Okay, now we need to change the sigma value in according to the SNRDB. Okay, so I can so this also can be achieved in many ways. Okay, okay, this can also be achieved in many ways. Okay, so I am going to tell you the simple way. Okay, so for example, if I get uh, SNRDB value, okay, SNRDB value, I get 0 to 40, okay, 0 to 30. So this is my SNRDB value, 0 to 30. Okay, now so AWGN, here there is no SNR value. Okay, so we have to change the power. Okay, so you know that this SNRDB is directly related with the power. How? Okay, so you can see that. So our SNRDB will be okay. So here these things again I am going to repeat. So SNRDB will be symbol power divided by noise power. So we set our symbol power to 1. Okay, we set our symbol power to 1, symbol energy to 1, and our noise power will be sigma square. Okay, so this is the SNRDB. Okay, so what is sigma? So SNRDB means here we are using 10 log 10, no? Okay, so so here we are using 10 log 10. Okay, so that is the dB value. Okay, so we have SNRDB is equal to 10 log 10 1 by square. Okay, so this, if I divided this SNR value by 10, okay, so this is 10 to the power. Okay, so so I get 1 by sigma square will be 10 to the power SNRDB divided by 10. Okay, okay, so sigma square will be 1 by 10 to the power SNRDB divided by 10. Okay, so so this is the sigma square, but in our random variable we have to put sigma. Okay, so sigma is equal to root, okay, root 1 by 10 SNRDB divided by 10. Okay, so this is the sigma. Okay, so I can write the sigma using the SNRDB. Okay, so here I have defined some SNRDB value. Now I am going to plot my bit error rate value with respect to this SNRDB value. Okay, so I will be having around 30 values. So if I run this, okay, okay, so we will have 31 values SNR 0, 1, 2, 3, 4 up to 30. Okay, so now I am going to calculate the bit error rate for every SNR value, for every this SNRDB value. Okay, before that I have to map this SNRD value with the sigma, otherwise I can't change the power, average power with respect to SNRDB. Okay, so we can see that the sigma is equal to square root SQRT 1 divided by 10 to the power, okay, 10 to the power SNRDB divided by 10. Is that correct? Am I correct? Okay, am I correct? So SQRT, the sigma should be SQRT square root of, so this is, I'm going to, so this sigma is equal to square root 1 by 10 to the power SNRDB divided by 10. Okay, this one divided by 10. Okay, so here this is 10. Okay, so I think I'm correct. Okay, so sigma is equal to SQRT 1 divided by 10 to the power SNRDB1. Okay, okay. And you can see now SNRDB are changing 0 to 30. And when it is changed 0 to 30, the sigma value will be changed. According to sigma value, this AWGN also change. Okay, so according to AWGN, this RX received signal will be changed. Okay, okay. Okay, so if I run this, here, so here this one, here this one, and we have to put another bracket. Okay, okay, now I think it is okay. So okay, so you can see that here we are asked to use this one. Okay, okay, when we are multiplying array, okay, matrix, multiplying or divide, we are multiplying or dividing matrix. Okay, sometime we are asked to use this this operator. Okay, operator. Okay, okay, because so that means we are multiplying or dividing all the corresponding point. Okay, all the corresponding point. So here if I put dot, it will be okay. Okay, and for safety, for every, so this will be array. Okay, so every division or multiplication, if you use the dot, it will be a it will not be a problem. Okay, okay, but here we are not asked to put the dot, but I show you, I put the dot here, so it will not give a error message. Okay, now here, yeah, so now what is that means? Okay, okay, we should be terminate. Okay, we have to terminate this one also. It is said that matrix dimension must agree. I will run it again. So metric dimension, this is Tx plus AWGN. Okay. So we have to error with this one. Okay. Yeah. Okay. Because so you can see that here, here we are generating only one. Only one actually, that in that time we have done this wrongly. Okay, because here we are going to generate only one bits, only one bit, 0 to sigma. Okay, so if you get the sigma, no, we are getting 0 to 30. So how can, okay. Okay. So you can see that here we have Rx value. We have Rx value. So we have received value. 100 received value should be there, no? Because we are using 100 bits. Okay. So 100 received value should be there. But AWGN, there is no 100 value. So, okay, I have to generate 100 AWGN value here. Okay, so if I put, I think we have done this. Okay, that is one row to n. Okay, so that is my number of bits. 1 to n. I think it will okay. It will be okay. Let's see. Yeah. No, 0 sigma 1 to n. Size information is inconsistent. What's that mean? 1 to n AWGN. What is the issue? So here we are using this one. Okay. Let's see. So I use this way, no? So it is okay. So what is the problem? Okay. So here I'm using some SNRDB value. Okay. Using some SNRDB value. Okay. Okay. So here we have 31 SNRDB value. Okay. 31 SNRDB value. And also we should have, okay. Also we should have, so if I comment this, okay, let's see. Okay, I comment this. Now I'm going to find the error, okay. If I write this, so yeah, the my matrix, yeah, okay. The problem is that, okay, so what is the problem here actually? Because here we have SNRDB, so that is 30 long. Okay, we have SNRDB, that array is 31 long. Okay, and so it will create a sigma array also. Okay, it will create a sigma array also. Okay, so that also will be 0 to 30. Okay, so here 0 to 30 values are there, sigma is 30 values are there. Okay, and we can't put this 30 values at in the same time. Okay, so I think that is the problem. So we can verify it. If I put some one value here, if I put one value here, so now it is okay, no? There is no any error message. So here I put dot here. Okay, so you can see that if I run this again, it will not have any problem. Okay, so we have some bit error. Okay, so you can see that SNRDB is very high, so there is no any error. Okay, so if I put very low SNR, so there can be some error. Okay, now you can see there is a bit error, no? If I put very low SNRDB, and if I put a very high SNRDB, for example, if it is 16, because there is no any error, no? Okay, so if I put 3 or something, that means very low SNR. Okay, so you can see some bit error rate is there. Okay, so you can see that okay, so I think you got the problem, you got the things now. Okay, so you can see that when we are changing this snrdb value, okay, this bit error is changing. Okay, so you can understand it how it happened. Okay, this snrdb value will change the power of this AWGN, and it change the impact of this received signal. So our decision may be wrong. Okay, so there can be some error bits. Okay, so that is happening now. We have to do, okay, we have to plot, okay, we have to plot this SNR from 0 to 1. Okay, so we can use a for loop here. Okay, so that means it is as a loop, so it calculating one by one. Okay, so I use for loop here. Okay, for loop here, for because without the for loop, if we define snrdb, so you will get that inconsistent problem, because this variables, this arrays, and this array elements, those are changed. Okay, so you will having that inconsistent problem. Okay, so in order to avoid that inconsistent problem, I will get for loops. Okay, so I will get for loops, and I get 0 to 30 or something. Okay, 0 to 30. And now it is as a for loop. So first, in first for loop, snrdp will be 0, and there will be some average power, and there can be some bit error. Okay, there can be some bit error. Okay, okay, so if I end this, okay, so I think now it will be not a problem. Okay, now you can see that we will have some snr value, and so we will have some answer, no? So the program is running. Okay, but the problem is that you can't plot. Okay, because you haven't snr, so you have snrdb value. Okay, no, here also you doesn't have snrdb array. Okay, so you don't have snrdb value. The value should be 0 to 30. Okay, and you also have the corresponding bit error rate also, okay. So how we can put, okay, we can put it in this way. Okay, so I think you can understand. Okay, still we can't plot, because the snrdb, this bit error rate is analyzing or calculating for 0 to snrdb from 0 to 30. Okay, but the snrdb value, the final value will be 30. Okay, and bit error rate is also, there is a final value that is 0. Okay, so only we have these two one. Okay, so when we are running this iteration, if we can how to say, if we can save that every value, then you can plot. Okay, so I can do it like in this way. Okay, so here we are calculating the bit error rate. Okay, we are calculating the bit error rate in every loop. Okay, we are calculating the bit error rate in every loop. Okay, then okay, I can do like this. Okay, I can generate another array. Okay, so this is so you can do it in another way. Okay, but this also a possible way. Okay, so I will assign a bit, I will assign an array. Okay, I will generate the array. Okay, array. Okay, and if I put, if I uh, if I uh, if I type like this. Okay, so first array name BER, bit error rate array. Okay, bit error rate array. Okay, and I use the BER. Okay, BER. So that means, okay, that means, so here, so for example, now you are starting this loop. Okay, so first SNRDB is 0. So you calculate some sigma value, then you calculate the AWGN value. So you have TX value already. Then you calculate the RX value for this 0. Okay, then you are decoding. Okay, you are decoding the received signal. Okay, received symbol. Okay, and you have decoded, you are going to decode it whether it is 0 or 1. Then you have decoded it. Okay, then you are compare it, the decoded signal with the message signal, decoded bits with the message bits. So if there is any mismatch, you calculate the number of error. So so number of error is divided by n. You calculate the bit error rate value. So here you have a value. Okay, so you put that value into this array, BER ARY array. Okay, okay. So you put one value here. Okay, you put one value here. Then again, after this, again it go to this for loop. Okay, so again, now SNRDB is 1. So in the same manner, you calculate sigma AWGN RX, then you calculate the detected bits, then you compare the detected bits between them. So if there is any number of error, okay, so it is calculated here, and it is the bit error rate is also calculated here, and you put that value again here. Okay, so in every iteration, it put in fill in the value to this array. Okay, so finally we will be having a BERARY array. Okay, this name array. So we will have all the bit error rate value, BER value, corresponding to this SNRDB value. Okay, so if I run this, undefined. Oh, okay. So before that, so you can see that before we have to we have to we have to uh, we have to define this. Okay, otherwise it will it will take as undefined value. Okay, undefined array or undefined value, undefined variable. Okay, so we have to define this array. Okay, so you can define this array at the beginning also. Okay, so you can generate an empty array actually here. Actually you have to generate the empty array. Okay, so you can generate the empty array like this. Okay, so this will be an empty array. Okay, this will be a empty array. Okay, so we don't know the size and we don't know the values there. Okay, it is empty array, just array. Okay, now so when it calculating the bit error rate in every iteration in that for loop, this SNRDB to 0 to 30, so it calculate bit error rate, some bit error rate, and it put into this bit error rate array. Okay, so we will see it. Yeah, so you can see that now BER array. Okay, so here you have 31 element, no? So you have some value. Actually, this is the bit error rate value. Okay, this is the bit error rate value. So this is the bit error rate value at 0. So you can see that. So SNRDB also. Okay, so now it is 30. Okay, SNRDB also 0 to 30 values are there. Okay, so here. So this is 0. The SNRDB is 0. It calculates this bit error rate. SNRDB is 1. It calculates this bit error rate. And this is SNR value is 3. 4. Likewise, you can see that when the SNR value is around 9, SNRDB value is around 9, 10, 11, the bit error rate is 0. Okay, so it calculate up to 30. Okay, it calculates up to 30. Okay, so here you have SNR value 30. So here the bit error rate is 30. Okay, now you have that bit error rate array. Okay, so bit error rate array. So it is corresponding to 0 to 30 SNR dB value. Okay, now you can plot it, but the problem is that here when we are running it in SNR dB in a for loop, so here SNR dB will not generate a array. Okay, so we have to generate the array here. Okay, so this may be a not may be not a standard way. Okay, but I will generate the arrays, the SNR value, because we have to plot this BER, this value. Okay, we have to plot this value. Where are they? We have to plot this value with respect to SNR dB. Okay, so this value is corresponding to 0 SNR dB, this value corresponding to 1. Okay, so 0 to 30 SNR dB value, corresponding values are here. We have to plot it corresponding to the SNR dB value. Okay, but here we don't have the SNR dB array, so we have to generate it. Okay, so here I am going to generate it. Okay, simply I can generate it, but this is not a formal way. Okay, anyway, you can generate it like this. So here you have generated this SNR dB value again. Okay, so if I run this, so here you have BER value, bit error rate value. Okay, and yeah, and here you have SNR value. Okay, so this will be your SNR dB value. It should be from 0. Yeah, it should be from 0. Okay, 0 to 30. So if I run this, okay, actually here my laptop is very slow because I am running another simulation actually. Okay, okay, now you can see that we have SNR dB 0 to 30. Okay, so we have SNR dB from 0 to 30. So we have SNR value, our independent variable value, and we have our dependent variable, that is BER. All that value is in this array. So this will be our dependent value, bit error rate value. Okay. So now the only thing is we have to plot. Okay. So here, don't use the plot command. Okay. Don't use this plot command. Okay. If you plot this, you will get, so your independent variable will be SNR dB. Okay, and your dependent variable will be BER ARY. No, it is in this array, so you have to plot this. Okay, so if you plot this, let's see what happened. Okay, okay, you can see that we will have like this. Okay, so so you have some bit error rate, and this is SNR dB. So you can see that we have some waterfall here. It is not very clear because we are using very few bits. We are using 100 bits. Okay, so if you are using 10,000 bit 1 lakhs bit, this will be very smooth. Okay, this will be a very smooth. Okay, but I think so normally you plot this SNR bit error rate value in log scale. Okay, so instead of this plotting, you can use semi-log, as I can remember. Okay, okay. So this will draw the graph in log scale. Okay, so we will see what happened. Okay, so you can see that it is in semi-log scale. Okay, so it is somewhat clear. Okay, so you can see that the waterfall arrangement is there. Okay, it is like there. Okay, so this is the simulation. Okay, so actually so this is your simulated value. Okay, and also you can calculate the theoretical value also. Okay, for that you have to know the BPSK bit error rate probability. Okay, BER probability. Okay, so you can define it using the Q function or error function. So if you know that, you can directly type this. Okay, you can directly type it, and you can so it is based on the SNR value. Okay, so you can directly uh, find the values. Okay, for this SNR dB value from 0 to 30, and you can plot that one also in the same graph. Okay, so you can compare it. Okay, so your simulated value with your theoretical value. So I think it is very simple. Okay, so I'm not going to do it here. Okay, so you can do it by yourself, try to do it. So it is very simple. You have to write the, you have to type the bit error rate equation with respect to Q function or error function. Okay, okay. So that is that. Okay. Mm, okay, so here this is I have write this program formally. Okay, so all so sometimes some codes may be changed, may be different, but conceptually almost codes are same. Okay, okay, but conceptually we have a same concept there. Okay, maybe different approach, but same concept. Okay, so you can see that here I'm generating a very high number of bits. Okay, so this n is my SNRDB value. I think the maximum SNRDB value. Okay, yeah, so here SNRDB -1 to I get from n, that means up to n 40. No, okay, so here so this is I just so this is my detected bit. Okay, received detected bit. Okay, so before putting it to the array, I have defined some zeros array here. Okay, so you can uh, you can uh, you can see, you can type this on the command window, and you can see what happened here. You will generate only zero array. Zero, there should be 10 to the power 6 zeros. Okay, in one row. Okay, so this will reduce some the some the array what is called sometime so this will, so if these arrays are changing with respect, if array is subjected to change, number of elements subjected to change in every iteration. Okay, so we can use this kind of, okay, so we will have fixed length array here. Okay, and here also that is I do. Okay, here also I do, and here this is array I defined to put that bit error rate theoretical value. Okay, and this array I defined to put bit error rate simulated value. Okay, so this is my message signal, and here I am doing the BPSK matching. Okay, now I am going to plot with respect to SNRDB. Okay, okay, and here this is the theory, bit error rate theory. Okay, so it is half error function SNR divided by 2 square root. Okay, so I type it here, I just type it. Okay, and BER theory also calculated, this value also calculated. Okay, and so for SNRDB from 0 to 39, I plot my the simulated bit error rate, it is in red, and my theoretical bit error rate, it is in blue. Okay, so I have limit the x-axis to get my drawing very clear, and I have also labeled the x-axis and y-axis, and I put legend, and I have put the title here. Okay, so you can also do this formal way. Okay, so if I write this, I think it will be a very good smooth. So you can see that it is very smooth, and so this red one is your so this, so you can see this pattern. Okay, so I have used a pattern here. What, so I use star here, that means it is a pattern. So that is my simulated curve. Okay, so that curve, and this blue one is the theoretical curve. So that one both are in same plane, no? So you will have so this simulation is 100% correct. Okay, so you can see, so these are the legend, this is the title, and I have used x and axis y label. Okay, okay, and I have also limit the x-axis. Okay, I have put some limits. So this is the limit for z-axis 0 to 40, and this is the limit for y-axis. This is the limit for x-axis, and this is the limit for y-axis. 10 to the power minus 1 to 1. Okay, so I have 1 to 10 to the power minus 5, and 0 to 40 x5. So I have limited. Okay, so you can use this code also. Okay, okay. So before end, I will give you a clue how to write a Matlab program to simulate the bit error rate in Qpsk. Okay, so you can see that in Qpsk we are sending 2 bits. We are sending 2 bits in one symbol. Okay, so these are the symbol. So let's say that this is S1, S2, S3, S4. Let's say that this is 0, 0, this is 1, 0, this is 1, 1. We have to use the gray code in here, 0, 0, 1, 0. So 1, 1. And here it should be 0, 1. Okay. Okay. Okay, so it is gray coding. Okay, so let's say that this is so bit so we assign a bit like this using the gray code method. Okay, so we have 4 consolation point. Okay, so you know that this value is 1 and this value will be 1. Okay, so here for symbol 1, you will have 1 plus j1. Okay, so this is your imaginary axis. Okay, this will be an imaginary axis. So S2 you will have minus 1 plus j1. S3 you will have minus 1 plus j1. S3 you will have minus 1 minus j1, 1j. S4 you will have plus 1 minus 1j. Okay, so these are your symbols. Okay, so these are your symbols. So you will have 4 symbols. So this is your transmitted symbol. Okay, and you have to assign, you have to consider, you have to take 2 bits. Okay, here in BPSK we have get 1 bits, and it map to -1 no +1. But here you have to get 2 bits. Okay, you have to get 2 bits. Okay. Matlab, you can do this. Okay, please check. You can use the internet and you can check it. Okay, so here you can get 2 bits. Okay, here you can get 2 bits, and you can assign these 2 bits into this symbol separately. So this 001 you can assign to 1 plus J1. Okay, so this 01 you can assign to this one is 4. Okay, that means +1 minus J1. Okay, so on. You can assign 2 bits to 2 bits to one symbol like this. So this symbol will be a complex symbol. Okay, complex symbol. Now you can send it through a AWGN value. Okay, so here you have complex value. Okay, so if you have generated a complex Gaussian noise, it will not be a problem. You can generate a complex Gaussian noise also here. Okay, and you can add it to the symbols. Okay, then you can decode it. Okay, okay. So when you are decoding, okay, when you are decoding, so here you have to use the Euclidean distance. Okay, when you are decoding. Okay, so that means say that you get a symbol here. So this will be your received symbol. Okay, now you want to decide this symbol is belong to this one, or this symbol is belong to this symbol is belong to this one, or this symbol is belong to this one, or this symbol is belong to this one, or this symbol is belong to this one. Okay, this received symbol. Okay, you have to check. How do you check? Okay, you have to calculate the Euclidean distance. Okay, you have to calculate the Euclidean distance. Okay, so here it is somewhat complex. You have to calculate the value from here to here. Okay, and you have to calculate the distance from here to this symbol, and you have to calculate the distance from this symbol. You have to calculate the distance to this symbols. Okay, you have to calculate that Euclidean distance. Okay, and if you have the minimum Euclidean distance, okay, say that you have the minimum Euclidean distance for this will be your minimum one. Okay, so according to this will be your minimum one. So you can assign, you can deduct this received bit as this. Okay, so it based on Euclidean distance. Okay, so that is how you should deduct the bit. Okay, so you have to consider the Euclidean distance here. Okay, now in BPSK we are using decision point, decision boundary, but here you can't use a decision boundary. You have to use the Euclidean distance. Okay, so this is you can do this in any modulation method. Also you can use the same method to BPSK also. Okay, BPSK also using the Euclidean distance. Okay, so if you have any point, you calculate the Euclidean distance from here to here. Euclidean distance to this symbol, and Euclidean distance to this symbol. So minimum distance, if you have minimum distance to this symbol, you deduct this symbol as this one. Okay, so that is you can use for any okay. So that is that. Okay, I hope you get idea. So if you have any problem, you can ask me. Okay, so I will wind up the session. Okay. Okay.